Natural language processing exists to solve a specific translation problem. It takes discrete, messy human language and forces it into mathematical space, converting a string of individual words into a single computable vector. The human brain handles this task effortlessly. We process language sequentially, absorbing one word after another over time to build a complete thought. Early artificial neural networks could not do this. Standard feed-forward networks process inputs independently. They have no internal mechanism to remember a word they saw 3 steps ago, making them ineffective at understanding a full sentence. To replicate human reading, engineers had to give the network a memory. They built an architecture that feeds its output back into its own input layer, passing data step by step alongside the new words. But forcing a machine to read sequentially like a human created a mathematical bottleneck. For years, this restricted how effectively these networks could process the relationships found in longer texts. The entire field had a wall known as the vanishing gradient problem. Every major architectural advancement in natural language processing since that moment is simply an escalating mathematical trick designed to bypass this specific decay. The first major attempt to maintain memory over a sequence was the Recurrent Neural Network, or RNN. It introduced the concept of a hidden state. This diagram shows the underlying math. The network updates its current hidden state using 2 inputs, the current word and the hidden state from the previous step. Notice this weight matrix W. The network multiplies incoming data by W at every single step. To process a full sentence, this recursive loop is unrolled across time. The result is a long chain of identical operations moving strictly left to right. When the network makes a mistake at the end of a sentence, it calculates an error. To learn, that error signal, the gradient, must travel backwards through the entire unrolled chain to adjust the weights of the earliest words. Computing those updates relies on the chain rule. Because the network unrolls sequentially, the chain rule dictates that you have to multiply the gradient by that weight matrix, W, over and over again for every step back in time. If the values in that matrix are less than 1, you are multiplying a fraction by a fraction repeatedly. The number shrinks exponentially. The learning signal physically decays to 0 before it can travel back to the start of the sentence. The network forgets the beginning of the sequence before it finishes processing the end. The math ensures short-term memory loss. The recurrent neural network is incapable of understanding long documents because it can never learn the connections between distant words. To fix this recurrent amnesia, researchers engineered the long short-term memory network, or LSTM. This schematic reveals the LSTM solution. It introduces a secondary path for data to travel called the cell state, a protected highway running straight through the top of the unit. Instead of repeatedly multiplying the memory by weight matrices, the cell state relies primarily on linear addition. This creates a channel where the gradient can flow backwards without shrinking. To manage what gets onto this highway, the LSTM uses 3 distinct valves, called a gating mechanism. First, the forget gate evaluates the current word and mathematically calculates exactly which irrelevant data should be dropped from the cell state. Next, the input gate analyzes the new word and decides what relevant new information needs to be added to the cell state. Finally, the output gate filters that cell state to pass only the most useful information down to the next layer of the network. A streamlined variant, the gated recurrent unit, or GRU, later emerged. It combines these gates into a simpler structure to reduce the computational load. LSTMs successfully preserved long-term memory.
But they were still forced to process data one sequential step at a time. Processing data sequentially creates a hardware bottleneck. Modern GPUs are built for parallel operations, computing thousands of numbers simultaneously. An LSTM forces the hardware to sit idle, waiting for word 2 to finish before it can process word 3. Engineers looked to computer vision for workarounds. They applied convolutional neural networks to text, scanning across a sentence with a filter to process multiple blocks of words in parallel. The drawback is the fixed window size. A CNN can detect a local phrase, but it cannot naturally connect a word at the beginning of a paragraph to a word at the end. Researchers also adapted the residual network, or ResNet, an architecture designed to solve similar problems in deep image processing. As this diagram shows, ResNets introduce the skip connection. The architecture creates a physical bypass. Data from layer 1 routes around layers 2 and 3,
adding itself directly to the input of layer 4. Like the LSTM's cell state, these skip connections allow the gradient to leap backward through the network, avoiding the chain rule's multiplication decay. By stacking parallel processing and gradient bypassing skip connections, the field was closing in on the core issue. The sequence itself was the problem. In 2017, the paper Attention is All You Need introduced the transformer architecture. It discarded recurrent loops entirely. Instead of stepping through a sentence word by word, the transformer uses self-attention. It loads every single word of a document into the network at the exact same time. To understand relationships without a sequence, it splits every word into 3 distinct vectors: a query, a key, and a value. The network takes the query vector of one word and computes the dot product against the key vectors of every other word simultaneously. This calculation generates a dense matrix of attention scores, weighting the relevance of every word to every other word. In this architecture, the mathematical distance between the first word and the 10,000th word is no longer 10,000 decaying steps. It is exactly one operation. Calculating this grid of relationships requires quadratic compute power, consuming significant memory resources. But because there are no sequential steps, the math is perfectly optimized for parallel processing on modern hardware. The transformer achieved long-range contextual awareness with 0 gradient decay, making every word in a document reachable in a single step. This diagram illustrates how transformers fit into the broader sequence-to-sequence framework. The architecture splits into 2 parts: an encoder that compresses input data into a context vector, and a decoder that generates the new output. Researchers soon realized they could isolate these components. Google used the transformer's encoder block as the foundation for BERT. BERT acts as a bidirectional encoder. It uses self-attention to understand the context of a word by analyzing everything to its left and its right simultaneously, improving performance on reading comprehension and sentiment analysis. OpenAI took a different path, isolating the transformer's decoder block to build the GPT models. GPT is a unidirectional, autoregressive model. It restricts its attention solely to the words that came before it, using that historical context to mathematically predict the next word in the sequence. Without the memory loss bottlenecks of recurrent networks, these models scale based on parameter count and training data, achieving human-like coherence. The modern AI revolution did not happen by perfectly mimicking the sequential biology of the human brain. It happened by abandoning that biology to engineer a mathematical environment where gradients can finally flow without limits.